We have discussed two sample location problems using Mann-Whitney statistic, and we have discussed two sample homogeneity using Kolmogorov-Smirnov statistic. In this module, we shall discuss a general statistic for dealing with two sample problems. Starting from the definition of ranks, we shall define a statistic which is known as a linear rank statistic, and later on we shall discuss some of its properties, including some summary measures, symmetry and asymptotic results. We start with the definition of ranks. Suppose Zi I running from 1 to n are n IID observations from a continuous population. Then the rank of the ith observation is the number of observations that are less than or equal to Zi. Then Ri, the rank of the ith observation, is defined as the number of observations that are less than or equal to the ith observation. That is, symbolically Ri equal to summation j from 1 to n indicator Zj less than equal to Zi. That is, as we have defined earlier, that Ri is nothing but the number of observations less than or equal to Zi. However, if the observations are ordered, that is Z1 less than Z2 less than up to Zn, then Ri is simply I. Now, we shall show how ranks can be described in terms of empirical cumulative distribution function. Note that by definition Ri equal to sum of the indicators Zj less than equal to Zi summing over j, and this is nothing but n times the ECDF at Zi. Again Ri is nothing but 1 plus summation indicator Zj less than equal to Zi, where the summation is extended over for every j not equal to I. Then we get that Ri can be represented as 1 plus Tzi, where Tzi is a function of Zi. Since the conditional distribution of Tzi is binomial with parameters n-1 and fzi, we get that the marginal distribution of Ri is discrete uniform over 1 to n. Next, we shall discuss how to obtain the joint distribution of ranks. Suppose x1, x2, xn are IID observations from an absolutely continuous distribution f, and y is the corresponding full set of order statistics. Suppose Pn is the set of n factorial permutations of the first n natural numbers. Then the joint density of x1, x2, xn given the full set of order statistics is 1 by n factorial, where x runs from x is any observation running over Pn, that is over the set of n factorial permutations of the first n natural numbers. Since x1, x2, xn is fully determined from the knowledge of the order statistics and R, that is the full set of ranks, and conversely we get that the conditional distribution of the rank vector given the order statistics is simply 1 upon n factorial for every value of R. Therefore, we find that the distribution of rank vector is independent of the order statistics vector, and hence we get the joint distribution of ranks as 1 by n factorial for all possible permutations of first n natural numbers. Now, it is interesting to observe that the distribution of R is independent of any f. That is, the distribution of ranks does not depend on the parent population as long as the parent population is continuous. Now, we can in an alternative way obtain the joint distribution of ranks. If we are taking observations from a continuous population, we find that the observations are distinct with probability 1. Then the joint probability of Ri equal to small r is nothing but the probability of the configuration xj1 less than xj2 less than up to xjn for some permutation j1, j2, jn belonging to Pn. Now, due to continuity, we get as earlier that probability rank probability of capital R equal to small r as 1 by n factorial for every possible value of R belonging to Pn. Now, next we shall obtain the marginal distribution of ranks. Now by definition, the marginal distribution of rank, say Ri, is probability Ri equal to small r, which is nothing but the summation over the joint distribution for every possible realization of the rank vector except Ri. And after a mathematical simplification, we find that this probability Ri equal to small r comes out as 1 by n for every possible value, say Ri equal to 1 up to small n. Thus, the marginal distribution is uniform over 1 to n, and we at once get expected value of Ri as n plus 1 by 2 and variance of Ri as n square minus 1 by 12. Now, if we want to find the marginal joint distribution of ranks, we can proceed as before, and in this case the range of the summation, the joint probability distribution of the rank vector is to be summed over all possible pairs except for Ri and Rj, and after summation we get that the marginal joint distribution of Ri and Rj comes out as 1 by n into n minus 1 for every Ri not equal to Rj. Now, using some routine algebra, it can be shown that the covariance between Ri and Rj is minus n plus 1 by 12, and hence the correlation coefficient between Ri and Rj is nothing but minus 1 by n minus 1. Now, it is interesting to observe that the correlation coefficient between Ri and Rj is negative. So, what is the reason? The reason is that if we look at the sum of n ranks, we find that the sum of n ranks is nothing but the sum of n first n natural numbers, and which is n plus 1 by 2. So, there is a negative relationship between Ri and Rj if the other ranks are kept fixed. So, we find that the correlation coefficient comes out as a negative. However, the above discussion and the above derivation is valid only when the underlying distribution is continuous. If we have some discrete population, then the ranks defined as earlier gives some misleading results. In fact, the distribution of ranks is not so simple when the underlying distribution is discrete. For example, consider n as 2. Then rank of Z1 has possible values 1 and 2. Again, according to our previous definition, rank of Z1 equal to 1 implies and implied by Z1 is less than Z2, and rank of Z1 equal to 2 implies and implied by Z1 greater than equal to Z2. Suppose Zi takes the values 1 and 2 with equal probability half for every I from 1 to 2. Consider the observed values 1, 1 and 2, 2 of Z1, Z2. Then we get, according to our definition, that rank of Z1 equal to 2 in each case. Thus, we get the highest rank for the lowest as well as highest possible observed values. Naturally, the above definition in the context of discrete distribution where values can be tied gives misleading results. So, we introduce in this case the concept of mid-ranks. If the underlying distribution is continuous, the two observations being identical has probability 0, but for discrete distribution, observations can be identical with positive probability. In practice, ties can occur due to the limitation of the measurement process. Since ranks in such a case gives misleading results, we introduce the concept of mid-rank. In particular, mid-rank is the average rank assigned to each member of a set of tied observations. So, let us illustrate the concept of mid-rank through a numerical example. There are 5 observations, and they are 2, 1, 4, 1 and 5. Then when we sort the observations, we get the sorted observations as 1, 1, 2, 4, 5, and hence the mid-rank assigned to the first 2 observations, that is the first actually the first 2 observations are tied at 1. So, we assign the mid-rank as 1 plus 2 divided by 2, that is 1.5. If we don't have any tie at the first position, at the first and second position, we could assign ranks 1 and 2, and if we find that there is a tie in the first 2 positions, then what we do, the mid rank is nothing but we add the possible ranks, that is 1 and 2 for the first two observations, and assign the average of these ranks to these tied observations. Then we get the modified rank vector corresponding to the shorted observations as 1.5, 1.5, 2, 4 and 5. So now we shall define mid-rank mathematically. For a set of observations zi I from 1 to n, the mid-rank is defined as Rk star, which is the sum of the indicators Zj less than or equal to Zk, so where the sum is running from j from 1 to capital N, minus n Zk minus 1 divided by 2, where n Zk is the number of observations equal to Zk. Thus, if we incorporate all these things into a one single quantity, then we get the definition of Rk star as summation j from 1 to n, indicator of Zj equal to Zk plus 1 whole thing divided by 2 plus summation j from 1 to n, indicator Zj less than Zk. So now we shall give a theoretical example on mid-rank, on the distribution of mid-ranks, because we have seen that the distribution of ranks when there are no ties is discrete uniform, and in this case we shall illustrate whether the distribution remains uniform or it is something different from uniform. So for example, suppose n equal to 2 and zi are IID Bernoulli P. Then we have the possible values of z1, z2 as 0, 1, 1, 0, 1, 1 and 0, 0, and corresponding to 0, 1, corresponding to each pair of z1, z2, we can calculate the observed value of the mid-rank R1 star and R2 star. So corresponding to the observation or realization 0, 1, we get the mid-rank vector as 1, 2, and this this observation, that is R1 star equal to 1 and R2 star equal to 2, has the probability P multiplied by 1 minus P. Again, if we have the observed value as of z1, z2 as 1, 1, then we get the mid-rank vector as 1.5, 1.5, and the probability corresponding to this is simply 1 minus P whole square, and in this way for the remaining possibilities we can calculate the distribution of R1 star and R2 star. Now we find that unlike the ranks in the untied case, here rank takes three possible values, namely 1, 1.5 and 2. So in case of untied observations or observations from some continuous distribution, we have seen that rank takes the values 1 and 2, but here we have some extra observation, we have some extra number in the list of ranks, and again the distribution is not uniform for any p belonging to 0, 1. Again, it is easy to observe that the marginal distributions are also different from uniform. Another theoretical example can also be constructed for when we have three observations and each observation is independent Bernoulli P, and here also we find that corresponding to the realization 0, 0, 0 of z1, z2, z3, we have the value of R1 star as 2 with corresponding probability 1 minus P whole cube, and when we have observations 0, 0, 1 for z1, z2, z3, we get the distribution corresponding probability as P into 1 minus P whole square, etc. Actually for n equal to 3, if the distribution, underlying distribution is continuous, we find that there are the possible values of a rank is either 1 or 2 or 3, but in this case we have the possible values 1, 1.5, 2 and 2.5, and it is natural that the marginal distribution is different from discrete uniform. Next we shall introduce the concept of anti-rank or inverse rank. If R1, R2, Rn is a rank vector, the anti-rank vector D is provided by the composite function R of D, which is nothing but Rd1, Rd2, Rdn, where this R of D or the composite function is such that it is the observations, it is the numbers in the natural form, that is D is the anti-rank vector if the composite function r of d comes out as 1, 2 up to n. So if we consider an example with n equal to 5, suppose r vector comes out as 3, 2, 4, 1, 5, then we get the composite function r of d as 1, 2, 3, 4, 5 only when d takes the values 4, 2, 1, 3, 5. Then in this case d is the anti-rank of r. Now we shall define a linear rank statistics. Since ranks form a basis for developing distribution tree procedure to identify the possible differences between populations, we shall use ranks for our purpose. For example, if one population has a larger location measure, then one can expect higher ranks corresponding to this population in the combined sample observations. Most commonly used tests can be expressed in terms of linear combinations of the function of ranks and indicator of the populations. Such linear combinations are termed linear rank statistics, and they can be used for a number of hypothesis testing problems. So now we shall give the formal definition. Suppose Zi, I running from 1 to n are IID observations from an unknown distribution fx, and we assume that f is continuous. Let Ri be the ranks corresponding to the observations Zi. Due to continuity, ranks are distinct with probability 1. A linear rank statistic is defined as L, which is the sum of Ci multiplied by A of Ri summing from I from 1 to n, where Ci are known as regression constants and Ai are known as scores. Note that now we shall discuss the usefulness of a linear rank statistic. The joint distribution of ranks is independent of any f. We have seen it earlier. Now, being a function of ranks, the distribution of L is therefore independent of any f. Hence, L can be used to provide distribution free tests for different alternatives regarding f. We shall discuss different choices of L for two sample location and scale problems separately. So we start with some properties of linear rank statistic. The first result is on finding the expected value of L. For a linear rank statistic L, expectation of L comes out as n times C bar multiplied by A bar, where C bar is nothing but the simple arithmetic mean of Ci's and A bar is the arithmetic mean of Ai's. Now, for a proof, we observe that expected value of L is by definition the summation over I from 1 to n Ci multiplied by expected value of ARI. Now, ARI is a random variable which takes the values A1, A2 up to An with equal probability 1 by n. Thus, we get expected value of L as summation I from 1 to n Ci multiplied by A1 plus A2 plus up to An whole thing divided by n, and which is nothing but n times C bar into A bar, and this proves the expected value for linear rank statistic. Our next result is related to variance of a linear rank statistic. For a linear rank statistic L, variance of L comes out as n square divided by n minus 1 multiplied by sigma square A into sigma square C, where sigma square A is the variance of AI's with divisor n and sigma square C is the variance of Ci's with divisor n. Now, observe that the ranks are not independent and L is a function of the ranks. So, variance of L, the different components or different summands of L are therefore correlated. So, we have to take into account that the different components of L are correlated. So, variance of L comes out as summation I from 1 to n Ci square multiplied by variance of ARI plus summation I not equal to j Ci Cj multiplied by covariance ARI ARJ. Now, after a messy algebra, we can obtain that variance of ARI is nothing but sigma square A and covariance between ARI and ARJ as minus sigma square A divided by n minus 1. Combining all these, we can get the result, that is the expression as defined above. Our next property is related to symmetry. For a linear rank statistic L, if either Ci plus Cn minus I plus 1 or Ai plus An minus I plus 1 is a constant for all I, the distribution of L is symmetric about its expectation. Note that the joint distribution of R1, R2, Rn is the same as the joint distribution of n minus R1 plus 1, n minus R2 plus 1 up to n minus Rn plus 1. Now, for proof, assume that Ai plus An minus I plus 1 equal to k for all I. Then a simple algebra gives a bar as k by 2. Now, the distribution of L is the same as summation I from 1 to n Ci multiplied by a n minus Ri plus 1. And again, the distribution of the last quantity is the same as summation I from 1 to n C di multiplied by a n minus I plus 1, that where di are the anti-rank vectors corresponding to the ranks. Now, we have already assumed that Ai is nothing but k minus a n minus I plus 1, and using this we get that L has the same distribution as the summation C di multiplied by k minus a I. And after just simple algebra, since summation over I from 1 to n C di is nothing but the summation over I from 1 to n Ci, we get that L and k n C bar minus L has the same distribution. Thus we get that L minus n C bar a bar by 2 has the same distribution as n C bar a bar by 2 minus L. And a similar result can be proved using the other condition, that is when Ci plus Cn minus I plus 1 is a constant, we can prove the same thing using some other type of mathematics. Now, we shall discuss the asymptotic distribution of linear rank statistics. You can check our presentation that there are given some conditions, say Wald-Wolfowitz condition, some Noether condition, and then Webb-Dim condition. And we have also seen that the Wald-Wolfowitz condition implies the Noether condition, and Webb-Dim condition is equivalent to the Noether condition. We have thus defined linear rank statistics based on the ranks of the observations in the combined sample. We have seen that rank has a distribution independent of the parent population, and therefore linear rank statistics form a basis for distribution free inference. In our next module, we shall discuss how a linear rank statistic can be used in particularly location and scale problems.